Okay, so welcome to this workshop on software-defined radio. I'm Didier Stevens, working for Enviso. So we are really going just to look at the basics of software-defined radio. We're not going to break anything or hack anything, just try to get a simple radio working. And we are going to work with GNU Radio. So, and it's a hands-on workshop. You will learn a few things just by trying to do it. So we will use GNU Radio. That's open source software for software-defined radio. But GNU Radio is not that easy to use. It has a steep learning curve. And therefore we are going to use GNU Radio Companion. And GNU Radio Companion is a kind of IDE, integrated development environment. So it gives you a GUI to build software-defined radios. And the way we are going to use that is with the live SDR environment. That's the USB stick that you got. So that is a live USB environment, an ISO, from which you can boot. The one you got here is just one that I downloaded. It's not the latest one, but it's the GNU Radio Live SDR environment. That ISO file that you download, and you can get it from GNU Radio. The only special thing about that USB stick is that it contains one sample, one example. Okay, one radio, a simple radio. That's what we are going to start with. So the dongle you got here is this one here, USB digital TV receiver RTL 2832U. So that is one of those USB dongles that you can use just to watch digital TV on your laptop. It comes with software so that you can watch digital TV on your laptop. Now the thing about this one here is that it has an integrated circuit inside which implements a software-defined radio, and this one here can be used with GNU Radio and GNU Radio Companion. Okay, so we are not going to use the stock software that was delivered with that to watch TV. That's not what we are going to do. We are going to use GNU Radio and GNU Radio Companion. So that's a site where you can find everything. And then also, I'm going to point you to that site here, Great Scott Gadgets. If you go to the SDR, Great Scott Gadgets, so that is from the guy who builds those dedicated software defined radios like the Hack RF1. And on this page here, SDR, you will find a lot of his resources for introductions to software-defined radios, like videos that he made, YouTube videos, about using his tools and software-defined radio. Okay, so we can start now. So you can boot from the USB stick, and once you have booted in Ubuntu, you can plug in the TV USB dongle. And then, in the root folder of the file system, you will find this file, one simple FM radio.grc. Okay, and you can open that file. Okay, and then just a remark: at the end of the workshop, I would like to get my sticks back. Okay, I bought them with my own money. A couple of years ago, I bought one on Deal Extreme. One of those Chinese websites where you can buy cheap stuff. I bought one, I tested it out, saw that it worked, and then I bought 20 of them so that I can give those workshops here. Okay. Okay, I have one more USB stick. So let me boot. But this this one, no, you can get it, but you see this one is broken. So it will work, but you will not be able to receive anything. Okay. Just try a stick from somebody else. So when somebody has booted in GNU Radio Companion, should work without a stick, and then try another one. Install anything, I just use the live boot option. So that's how it looks here. Let me share my screen. Yeah. Huh. Yeah.
Yeah. Is there anything needs to be changed? Every boot with its rights.
And if you can you go? Oh no, indeed. You could try another stick because I use it on a Mac too.
Yeah.
Okay, so I'm sharing my screen. So this is also the screen you would get if you would boot from that ISO, from that live CD, if you just downloaded it from the GNU Radio site. So this is Ubuntu, and you have the GNU Radio Companion installed here. Now, if, like me, you don't have a UK or US keyboard, and you're not familiar with Ubuntu, you can change the keyboard here. See here, I have E and English. I can click on that to change my keyboard layout. Here in text entry settings. And then here you can add your keyboard. Okay, so I'm going to add a Belgian keyboard. And I'm going to remove the UK keyboard. Okay, so in case you don't have a US or UK keyboard, I don't actually, a UK keyboard, is it, I know it's not completely the same as US keyboard, but can you work with it? When, yeah? But we won't have to type a lot, just a bit of numbers, and then it's easy when you have the right keyboard. So we can close this. I can plug in the TV dongle. The blue LED should light up. And then Here you go to your file system, and in the root here you can find that file. So that's a simple example that I made, one simple FM radio. Okay, so you can open that. Okay, so this is the GNU Radio Companion I'm seeing here. And you can see different components that I put in here. We'll talk about them later. We are just starting already with that, just to check out that everything works fine with you and with your system. Okay. Once we know that, then we will go into building our own simple radio step by step. So I did this in my room, and I got fine reception. Unfortunately, in this room, not. I think there's too much interference from all the transmitters and all the computers, but maybe we'll still find something. So I'm going to turn this on. I'm going to run this, and you can do this here with this play button at the top. Okay? And then you get static. If you get static, then it works. Okay. I had good reception of a local radio here, 89.1, but here in this room not. If you want to try it out, so here on the Osmocom source, yeah, this block, double click this block, and here you can see a frequency in hertz. 1,600,000, that's exponential notation. So that's 100.6 megahertz. Okay, a million of hertz, megahertz. That's a local station in Brussels, works well in Brussels, but not here, of course. And what I had good success here was 89.1 here. But again, in this room, when I just tried it, it was not so fine. Maybe for your machine it will be a bit different. You can try it out. See, but I still get static, even when I try to be an antenna myself. 100.9, okay. No, no. Yeah, and if you want to stop it, here you have the stop button after, next to the play button. Okay. Are you having a problem? Oh yeah, okay. How about you're up and running? Okay. Fine.
How patient do you reckon?
The USB sticks, yeah. Okay, so this diagram here, going to explain that later, but so this is how you build your definitions of software-defined radio and the way you play with it. So when you play that software-defined radio, it's with the button here, play. Now, if we go into a shell, and I do less of that file to look at the input, you can see it's actually XML. Okay, so that GRC file, that definition file for GNU radio companion is an XML file. And if we go through it,
My machine's radio happy running without the USB stick in it.
Yes. Yeah, you notice any of that.
okay, you see here, for example, this is the megahertz that we entered. So it's an XML file, a GRC file. Now GNU Radio Companion, GNU Radio. GNU Radio is a set of libraries that helps you build software-defined radios by programming, by building programs. And typical way of doing this is to program this in Python or in C, C++. Okay? But you can avoid having to program in those languages by using the GNU Radio Companion. Now, if you look here at the output of the GNU Radio Companion, here, if you scroll up a bit, you can see generating temp topblock.py and executing temp topblock.py. So it's actually, GNU Radio Companion is actually, by using this diagram here, building a Python file for you, generating a Python script, and then executing that. So we can have a look at that one. So in the temp folder, here I have topblock.py. And this is the Python program that was generated for you. So before GNU Radio Companion, users of GNU Radio had to write this by hand themselves. Could not use a generator. And here, for example, you can see the frequency that I set. You can execute this program too from Python. You don't have to run it inside the GNU Radio Companion environment. You can just run it from Python like this. Sorry, it's. You want the tab bigger or the font bigger? Font, yeah. Okay. Is that in settings? It's in the actual terminal? Yeah. Okay. Ah, yeah. Yeah, view. Would zoom in work? Yeah. Is that good for you? Want it bigger? Oh. Okay. So I have the Python program here that was generated by the GNU Radio Companion. You can look at the code and you can execute it like this. Just run Python, the same, and then you get the same effect. You can stop it with Ctrl+C. Okay. So now before we start building our own radio here with those blocks, we are just going to build the same radio and then improve upon it. Before we do that, I already want to show you some things you need to know about GNU Radio. For example, about those arrows here that create connections between the blocks. So you can select an arrow like this. Yeah, I double clicked it so it disappeared. This one here too, click, disappeared. Otherwise here you will have a button here, delete the selected block. You can use that too to delete the connection. And then to create a connection again, you first click on the output, here out, and then on the input here, and then it draws the arrow. Okay? You can remove the arrow again. Yeah, here. So I was able to select it once, and here you see I can delete it. Move this one out of the way, and then connect these ones here. Okay. You can see that this time the arrow is red. Okay. It means that there is a problem. I will explain that later. The colors are different, so you cannot just connect them directly. Okay. Here you see it was blue blue, so that could be enabled. And here orange orange, that could also be connected. And when you have errors in your file, then you are not able to run it, and you get a warning here. You can click on that warning to get more explanation. But that's the kind of explanation you get from GNU Radio. So kind of cryptic, not explanations from GNU Radio Companion. Okay. Also, if you noticed, blocks that have problems, errors also are in red, like this one here. This one is red because it's not connected to anything. You can, if I build up my diagram again, so I remove this, you will see here I will remove this connection and those two will become red. Like this, you see, because they are not connected. I make those two are red, I make a first connection. Okay, this one now is black. This one is still red because it still has a connector that is not connected. I can still not execute it. And if I connect them like this, then it's connected, nothing is red, and now I can run it. Okay. So that's the most important thing you need to know about connecting these things. Okay, so that's why we started here with this diagram. And now we are just going to make our radio from scratch. And I'm going to explain step by step how this works. So you create a new file here, a new flow graph with this icon. Like this. And when you do that, only two blocks are generated for you. Okay? One with the options and one with a variable. Okay? We are going to change the options, so you can double click options. You see here the ID is top block. That's why the Python program was named top block, because it's the ID of the options. What I'm going to change here, and you do that best too, in generate options, we are going to use another GUI, the WX GUI. Okay? And then you can accept this. So that is our first change. Now we can leave this block alone, this is fine. This block here defines a variable, the sample rate. So we are dealing here with digital radio, so that means that, of course, it's not analog radio. Analog radio works with analog signals, and they are not discrete. Those are not discrete values, those are continuous values that change continuously. When you are dealing with something digital, you are dealing with something discrete, different numbers, and they change usually from one set to the other. So one byte, another byte, and so on. And that's how your stream of data in a digital world is built. Now to convert this, to get from that analog world to the digital world, we need a converter. So an analog radio has quite a few components, like for this FM radio here. Yeah, and the reason why I'm using an FM radio here, it's about the most simple device that you can build. An AM radio, amplitude modulation radio, would be even simpler to make. But the thing is, those devices don't support it, and also you would almost find no more stations that broadcast in AM. Now it is FM, and FM is also quickly reaching its end. I think in a year or two, for example, in Belgium, they will also stop FM broadcasts and only have the digital broadcasts. So we are dealing with something analog that we are going to process digitally. So an FM radio has several components. So first of all, an antenna to receive the radio frequency, the radio signal, and that signal then needs to be decoded into something you can hear, and to an audio signal. And there are several components there. For example, there is a component that will amplify the radio signal that is received. There's a component that will allow you to tune into the frequencies you want to listen to. There's then a component that will demodulate the signal, FM demodulation. Then a component that will amplify the audio, and another component that will play the audio. So all those components make up an analog radio, analog FM radio. In a software-defined radio, a lot of those components are going to be defined in software. Okay? So for example, the FM demodulator, it will not be built in hardware, and you will do it with software. And that's what we are going to do here. So simply put, the device of a software device defined radio that gives you the data stream that you can process, simply put, it has just an antenna, a tuning circuit, but much broader than what you would have in an analog radio, and then something that converts that analog data to digital data. Okay? And that's an AD converter, analog to digital converter. And an analog to digital converter takes a continuous signal and produces a discrete signal. And you have to define the speed at which it has to do that. For example, every second. Take a sample every second. Now that would be good for a very slow moving signal, but nothing like audio or radio or anything. Audio, for example, what we speak, if I'm not mistaken, it's between 100 Hertz and about 15,000 Hertz, if I'm not mistaken. But no, sorry, speaking, no, between 300 and 3000, sorry. I was talking about music and things like that, what we hear. Okay, but so what we speak is about 300, 3000, and so that's in Hertz. That means that you have if we are talking about 300, the lowest frequencies, about 300 changes per second. Okay, so if you would sample only once per second, yeah, that would not work because you have too much changes in your time between you are waiting for your next sample. Okay. So you have to sample at a speed that is high enough for what you're going to capture. And that is here the purpose of this variable. The samp rate, you can double click this and you can see that it is set to 32,000. That's the default. But that is way too low for analog radio. For the FM radios we are going to capture. Our device that we have here can go about to 2 MHz as a sample rate. Okay, so we will use that But we will not use exactly 2 megahertz, not 2 million, but we will use something closer by, and I will explain you later why we do that, and that's 1,920,000, like this. That's a sample rate that we are going to use there. So that is the sample rate that we will use to produce digital data from our software-defined radio. Okay. So that set can work with that. And now we are going to add our radio. And here, in the right hand, is there a problem? Yep. Oh, it's making a lot of noise now. Okay. Here you can go in the right hand into sources. And here you have the Osmocom source. So that defines a software-defined radio device, and you can drag this into your diagram. So it's put in your diagram. It's red because there's an error, it's not connected. And you can see already a couple of values, like 100 megahertz, that's the frequency, the default frequency it will operate on. And then you can see your sample rate, and sample rate is 1.92 megahertz. So the value that we gave it here, this variable. And the reason why that is, if you double click on it, you can see here the sample rate is not a number, but it's a variable. The variable that we defined here. Okay? Sorry? Sorry?
Could you repeat the name of the source?
Ah, yes, of course. Osmocom source here. Osmocom. This is the first one in sources. Okay? There are many more parameters, but we don't need to touch them. So what you're actually doing now is writing a kind of program. And when you run this, this will generate a Python program like we saw. So that is our source. So that will enable us to select the radio signal in the FM band, for example. And then we will get that raw FM band. And with this parameter frequency here, we can tune what we want. But you will not get only this, and depending on the bandwidth of your device, you can get several megahertz to the left and to the right. This here, again, it's not a very powerful device, of course. So we won't get much, but it's still good enough for FM radio. If you double click again, here with output type, you can see complex float 32. Okay, so that tells us that the data we are receiving are actually complex numbers. So a complex number, maybe you remember that from your math classes. So it's composed of a real part and an imaginary part. Okay, so a complex number is two numbers. A real part, just a real number, like 1.2, and an imaginary number. And an imaginary number that is based on the standard imaginary number I. And I, you cannot express what number that is, but it has one property. If you take the square of I, you get -1. Okay? So it's not a normal number, it's not a real number, because you cannot find any real number that you would square and then get a negative number. All integers and real numbers that you square, you always get a positive number. But the imaginary number I, that's a special one. If you square that, then you get -1. Okay. And so a complex number is just one number, a real number, and one imaginary number. Okay, why is that? Because in electronics and also in transmission technology, signals like this can be mathematically described with complex numbers. Okay? So you have a lot of formulas to operate on signals, and they work with complex numbers. And that is why we are here in this device also working with complex numbers. The radio frequency signal that we are receiving is a stream of data, and those are complex numbers. That's the output. And that is also why we have here that blue output. The blue tells you that it is a complex number. And now you can also understand why we were not able to connect it to that. The other one, well, that other one is probably not a complex number, the orange one. Yeah. Okay, so we have our radio signal just out of the ether, not processed. And now we want to decode it. We have here to do demodulation. So with FM radio, we are talking about frequency modulation. And modulation is the following. Modulation means that you have your carrier signal, so one frequency you are transmitting, for example 100 megahertz. And if you would not do any modulation, that would be, well, simply put, that would be the pure frequency that would be put out. And precisely 100 megahertz and nothing else except for harmonics, but let's not talk about that. So that's what you would get, just one thing. Now, to encode data on that carrier, to encode signal like audio, like music, to encode audio on that, there are several techniques that have been devised. The very first one that was devised was the Morse code. That was actually the most simple one, method of encoding. If you want to encode something, well, you transmit and then you stop transmitting. And then you start again. And the durations of those transmissions tell you information, the dot and the dashes. That was one of the simplest way to encode the signal. Just stop transmitting the carrier wave for a short period of time and then transmit dots, dashes, like SOS, for example. Another one that came a bit later is amplitude modulation. And modulation means that you are going to modify the property of your carrier wave according to another property, for example, an audio signal. So you are going to use an audio signal to change your carrier wave. And what we are going to change here of the carrier wave is its amplitude. Okay. So the amplitude of the wave, if you have a carrier wave, it has a standard, a default, a non-changing amplitude. And if you modulate that, it means that you will make the amplitude change, make it smaller or larger, depending on an audio signal, for example. Okay. So if your audio signal is strong, then you will use a large amplitude. If you have a low audio signal, a low amplitude. Okay. And that's how you can easily encode audio signal into a carrier wave with AM. FM, frequency modulation, it's another method, but there instead of the amplitude, it's a frequency of the carrier that is modulated. Okay? So, for example, we are transmitting at 100 megahertz. Well, we will make some changes to it according to the audio signal. Simply put, for example, if I have an audio wave of 1 kilohertz, then I would transmit on 100 megahertz plus 1 kilohertz. It's not as simple as that, but that's the gist of it. Okay. So, FM modulation, we encode a signal into the carrier wave by manipulating the frequency. And that's what we get here when we tune in into an FM radio. We get here radio signals that are FM modulated. So to hear the audio, we need to demodulate it. For that you have also blocks. In the right hand here you have modulators. You see here at the top amplitude modulation. And what we are going to use as an FM demodulator here is found at the bottom, WB FM receive, wideband FM demodulator. Okay. So you can take this one, WB FM receive, and drag it into your diagram. It's here. If you double click on it, you can see those two parameters. For this type of demodulator, that's the parameter that we need. I think in advanced here, no. Okay. So here for the quadrature rate, you can just put in your sample rate. Okay, so the variable samp underscore rate. You can also see that here, this is first in red. So because it has no value, but if you type something, its color will change. So this WBFM receiver works with a quadrature rate and an audio decimation to do the demodulation. Those are two parameters that you have to provide. And for the quadrature rate, you can provide the sample rate. And then the audio decimation, that will be a number, an integer, that will be used to divide that sample rate. Okay? And we are going to use 40. And I will explain you why. So, this will do the demodulation, and the output of that will also be at a specific sample rate. Okay? But audio goes about to 20 kilohertz, yeah? And most people cannot hear that 20 kilohertz. I think about 11 or 12 years ago when I started my blog, I did a small experiment. I could hear 17,000 kilohertz if I'm not mistaken. Now at 10 years later, I'm sure I'm no longer able to hear that, maybe, if I'm lucky, 15,000. And if you want to test that, that's something you can test. You can find here also audio generators, for example, signal generators that will generate you sine waves, and then you can connect that to the audio output and hear that. Okay. So we want to downsample that, and we are going to downsample that to 40, so divide it by 40 to get a lower sample rate, a sample rate that is better for audio. And now I can tell you why I selected here as a sample rate 1,920,000, because if I divide that by 40, then I end up with 48,000, okay, 48 kilohertz. And 48 kilohertz is a sampling rate that is often used for audio. Okay, so we can close that block. So that is important to understand, that you have your sample rates, and if you are going from radio frequencies to audio frequencies, that you have to work with different sample rates. We will experiment later a bit with those sample rates and see what the, well, actually we can already do that now, sorry. Let's just go back to this one here. So here I have my radio, I can play it, and I have static, this static. If I increase the sample rate, for example 10 times more, that's not something that device can handle. You see, then it is interrupted. It cannot sample at that frequency. Also, if you go too low, like this, then also get sample problems. So that is important to figure out the right sample rates. And here, okay, I can work with 2 million, but since I knew beforehand that I'm going to work with that FM demodulator that does downsampling by dividing by an integer value, I just selected here the right value to end up with 48 kilohertz. Okay, so if you want to make the calculations on another device, you can do the opposite. You want to end up with 48 kilohertz. For example, you know that your device can go up to 10 megahertz. Then you divide, then you multiply that 48 megahertz by a number to get around 10 megahertz, and that's the number you will here then use. Okay, so now we can connect this like this. And now here we have an audio signal coming out. You can listen to that audio signal with an audio sync. So if you go at the top into audio, you have here an audio sync. So these are sources. They consume your data from devices like the software-defined radio device, and then you also use sinks. Sinks, they produce output. For example, an audio sync is connected to your speaker. So you can drag this into the diagram. Orange, so we can connect this one. You can see the sample rate, 1.92 megahertz. That's way too high for audio. So you can double click this and open the pull down here. And here you can see 48 kilohertz is one of the proposed ones. And you also have the 44.1 from CD quality. So you can select this one and then just connect. And now you build your radio. Let me try again here with, it was 100.9, eh? Yeah. Okay. So I'm trying to use an extender cable to get away from my computer, but it doesn't help. When you run this for the first time, it will ask you to save the file, because we did not yet save the file. We just created the file. So you can give it a name, test. And then it will run it. So that is a basic FM radio, a receiver at a source, the speaker, the audio sink, and here the demodulator. And the only thing you need to pay attention to is sample rates. Now, this is not very useful as a FM radio, for example, here that you have to stop this and then edit this frequency value to tune into different stations. Now, you can create variables for that. So here, if you drill down, at the bottom you have variables with a couple of different types of variables, and we are going to use the variable here. Okay? So you drag this into your diagram. Double click it. And then you call it frequency. And 109 E6. Exponent 6 means 1 million. And now if I go to my source and nothing has changed, it will not use this variable. You have to open the source and change the frequency to that variable name. Any idea why I'm... Okay. It's stable now. It's no longer. Yeah. Thanks. So I double clicked here the source component, and here I have my frequency, and here now I can type the name of my variable, frequency. Like this. So remember that I told you that GNU Radio Companion here is generating Python programs. So what you are typing here are actually Python expressions. So here just the name of a variable, but you can do different operations with it. For example, you would be able to do *2 to have the double of the frequency. That's not something useful here, but there are cases where you can do conversions. For example, some of these fields will expect an integer, and your variable will be a real number. What you can do then is say, okay, int of frequency, and just with a Python function int to convert something to an integer. And you can type Python expressions here. But here we just need the frequency, that's all. Okay. And now when you run this, it is using this variable. Okay. Now that's a bit of an improvement, but not much, because you can try to change this. See, but not much happens. If you want that, if you want to be able to change it, for example with the dial, then you are going to use extra elements for the GUI. We are going to introduce a graphical user interface. So here we were using one for the definition, but we were not using one for playing, for executing the code. You can also add graphical components when executing the code. And that's when it becomes very powerful to use a software-defined radio. So we are going to use that, and we have to look here into GUI widgets. So remember we selected WX GUI, so drill down to WX, because those are the components that we are going to use. And what I'm going to use here is the WX GUI slider. That allows me to give me a slider that I can use. So you can drag this onto the diagram. Yeah, so under GUI widgets, WX GUI slider. And this one here will replace our frequency variable. So we can delete this variable like this, and then you double click the glider, and you say now that the variable, that the slider name here, sorry, is frequency. So that defines a frequency. And I'm going to go with my slider from 80 megahertz to 108 megahertz. So from 80 megahertz to 180 megahertz, that gives me 28 megahertz, and I want to be able to tune in with 100 kilohertz. Okay, so that means if here I can say the number of steps that I want between those two values. If I say 28, yeah, then I can go from megahertz to megahertz. If I say 280 and 10 times more, then I can go from kilohertz to kilohertz. So that's what I'm going to use. 280, because 28 is the difference here, and I multiply with 10 to have 100 kilohertz steps instead of 1 megahertz steps. And then the default value, of course, 50, that's not a good one. Let's say that we start at 100 megahertz, like this. Okay. So, and if you did that correctly, everything should be green and you should be able to play. And now you can see here, this dialog box appeared, top block, with my slider. And I can use that to tune in. See? You can also click on the left and right arrows to move 100 kilohertz step by step. I'm not getting anything here. Oh yeah, this here, yeah. This one I had in my room too. This is a single carrier wave, looks unmodulated, and you see it produces silent. Well, almost silent. Well, it's unfortunate. I had several stations in my room. No. Is anyone able to get something over radio? No. Yeah, no. Yes, I tried that here with the extension cable, but it didn't work for me. In my room, it did better, even better than at the window. But actually, around noon, I even tried to simulate an enclosed room like this, and I went with all my gear into my bathroom. And it worked, but of course not that well. But still, I could hear some talk, some music now, fortunately. But let's not despair.
Can you emulate the radio?
Yeah, I think you can. I think you can. But I don't think then you will have the interesting features that, well, I mean, emulate, you can inject a wave file. Okay? But then you won't get the interesting features that we could get with the real radio. Because, so, I'm going to introduce a couple of other interesting elements. So if you go to instrumentation, you have, again, QT and WX. We will use WX. In instrumentation, you can add instruments to your radio and observe what is happening inside. And now you will see the power of this GNU radio environment and software-defined radio. For example, we'll use a fast Fourier transform sync so that we can see the visualization of the frequencies. Okay, so you can drag this onto your diagram. You see that it automatically took the sample rate here. That's why it's useful to work with that variable, because components like these will take over that sample rate automatically. And now you can connect this like this. Okay. Now, this already is something very special. Just the fact that you can say, okay, I have my output here that goes to my demodulator, and now I'm going to take that output and put it in something else. Yeah? That is trivial to do with software-defined radio, like you see here. But to do something like that with real radio is much more difficult, because those signals, you have to match impedances and other characteristics of those signals for input and output, and you cannot just throw in other stuff like you would do with digital electronics or analog electronics, but at a lower frequency. When we are talking about radio frequency technology, just creating a print with a layout that works fine is already an art. It is not that easy as just creating a print for an analog circuit for an Arduino, because you have to take into account a lot of things that can go wrong. So, for example, analog radio is really relying, for example, on components like inductors and capacitors and things like that. If you just put two traces, copper traces, on a printed circuit board next to each other, that works fine in a classical electronic environment, but when we are talking about radio frequencies, those two are already creating a very small capacitor. And that very small capacitor can influence the behavior of your circuit because you are working with frequencies that are that high. Okay? Very small changes in capacity and inductance, they can have a big influence on your radio, in your circuit that you're building. That's something, big advantage that you don't have here in software-defined radio. You can just drag it in, connect it, and it will work. So we can play this. And now, if you tune, maybe you will find yeah. This is the silent I was talking about. So that's, yeah.
I already tried to remove it and edit again, but
Can you play it and show me what's happening?
keep getting this -7 in 10 codes.
Oh, -7.
I already tried to remove and edit again.
Mm-hmm.
It's curious.
Yeah. Yeah. So, no, it will make it too. The thing is, you cannot remove connections and leave things unconnected, and it will not work.
Okay.
And you took it from instrument tape. Yeah, that's the one.
Yeah.
Can you?
Yeah.
Let's go to this radio and try it here.
Okay. Yeah.
Same. Okay, so that's something else here. No, I've never seen that before.
Yeah. Okay.
No, sorry. Yeah, also -7. Strange. Okay. Ah, you have somebody has music. Yay. Well, let me mute mine.
Very soft. Soft though.
So that is something that I also had in my room at 186.4 megahertz. I have a carrier wave here, okay, unmodulated. If you select that one, first of all you can see the peak here. But also if you play the audio, it's much less noisy than the surrounding, and that's because it's unmodulated. So for when you demodulate it to audio, it's like there is no sound as silence. Can stop this. Another nice one to add is a waterfall sync. So maybe for the people who that didn't work, just remove that FFT, the fast Fourier transform sync, and try just with a waterfall sync. Oh, I'm just thinking about something. You did change this variable, WX GUI? Yeah? Okay, no. It's not that. Yeah, I have no idea what that is. I mean, I've given this workshop a couple of times and never had that problem before. And you're using just my stick and thing, yeah? Yeah. Sorry. Okay. So you can drop in that waterfall sync and connect that one too.
Yeah, that's what mine did. It works once or twice, then it's maxed out.
All 4 cores on my i5 going flat out.
Okay. So here you have that waterfall slide. So that is something that evolves with time. Here you can see the number of seconds. So that was 16 seconds ago. And the colors that you see here is the energy of the radio signals captured at that frequency. Same frequency as is here. So if I go to that 86.4, yeah. You see this one here, now this one here is drawing a green line. Okay? And with FM radios, you also get that, but that line is blurry. Okay, it's not a straight line, but it's a blurry line. And that's how, in my room, I was able to tune in into different radio stations just by looking here at the diagrams. And you see, it is that evolves in time, and that's me moving the frequency. Okay, I'm trying again now with the extension cable. I'm next to the window. Oh. Yeah, now you see I'm getting a bit more. You see, I'm getting some faint lines. See, those are radio stations. But even if I'm tuned into them, oh yeah, I can hear them. I can hear a bit of music. Let's try this one. Yeah, I have a signal here. I can hear a bit of it, and that's at 100.9 that you told me. You see, here is a signal. What do you have? 91? 91.3. Okay. No, that one is weaker for me. You see? You can see that on the graph. Here it's more green than here. That's the advantage of that water flow graph.
So if there's a green line, there should be thumbs up.
Yeah. Okay. So those are very useful and powerful tools that the GNU Radio Companion provides you with. I mean, spectrum analyzers like this and also oscilloscopes like this, they don't run cheap if you have to buy them. If you want to work with real radio, but if you're working with digital radio, you can get those tools for free. And they're also easy to implement, as we saw. I'm going to stop, and I'm going to add one more waterfall sync. And this one here, I'm going to make it watch the audio output. Okay? So I connect the audio output with this one here, and you see that will not work. Because we have orange, blue. Yeah? So you have to double click that one and say that you want to work with float numbers, not complex numbers. Okay? And then also the sample rate is not good. And the sample rate of our audio is not the 1.92 megahertz, but it's a 48 kilohertz. So you have to adapt the sample rate. So those are things you always have to pay attention to, and with software-defined radio here in GNU Radio. The sample rates of the different components and also the impedance matching. So, and now that I've configured my second waterfall sync like that, I can connect the audio like this. But let me stop. I will make a small change here. In my slider I will say that the default value is 100.9. That's where I'm getting the best signal. Yeah. No, okay, I'm getting a signal here, but here, this is just noise, you see. You don't see any structure in there. If there would be music or a sound or voice that you would recognize, then you would see a different, because this here is the time and this is the frequency, up to 20 kilohertz here. Yeah. When it's turning gray like that, it's processing too much. That's because of all those. Yeah, it's back. So I will stop this and throw out the FFT.
Would you like to try the antenna that I'm using?
Yeah, I could try that, yeah. Is it the same connector? No, I think it's, yeah, it's not the same.
This side? Or you just want to try the area?
Yeah, good idea, thank you. Yeah, we are getting something better now. Yeah, I have a bit of music, thank you. Okay, so what we are seeing here, the waterfall plot of the radio frequency, and here the waterfall plot of the audio. Here you can see a bit of structure here, small changes. That's the music that I'm faintly hearing. And you also see a line here. Any idea what this is? If you look into it, you can see it's 19 kilohertz. No? 19 kilohertz?
Actually, it's a frequency generated by the radio itself.
No. This one here is the pilot wave for stereo. So if FM is broadcasting in stereo, then you have a pilot wave at exactly 19 kilohertz, but in the audio, okay? Not in the, well, actually also in the RF, because it's modulated into the RF, but here in the audio, if that is present, then you know that you have FM radio. And the FM radio then starts at double that frequency, so at 38 kilohertz. That's the other component of the FM radio. But it is not just left-right, because this stuff was devised a long time ago when people had FM radio without stereo. And when they introduced stereo a long time ago, introduction of stereo. What you wanted, of course, was backwards compatibility. That when the broadcast systems turned on stereo, that people with older radios would still be able to buy a new radio. Still be able to listen to the radio without having to buy a radio. I mean, it's not, you see, it was not an idea from Apple. This was made by engineers who had the best of people in mind. So they wanted to build something. And so actually this is not left-right, but it's a combination of left-right and then the difference. Okay, so that you can subtract and extract the two channels. And if you don't do that, well, then you have just a mix of the two. Okay. Okay. So those are things that you can do with instrumentation and GUIs. Now, I'm going to show you a couple of other simple operations you can do. For example, amplify this audio signal here. Okay, so analog radio, what would you need to do? Built in an audio amplifier, something to amplify your audio. Here, we are just talking bits at data. How would you amplify that signal? It's just numbers. And you want to make them bigger. Multiply. Yeah. Here you can just multiply. And that will make it louder. It will amplify it. And in your sliders here, not your sliders, I mean in your overview of components here, you have MAT operators. See? Absolute value, add, multiply, things like that. And you have several multipliers. A multiply by matrix conjugate, constant. The constant, that's what we actually want. We want to multiply with a constant value. Okay? So you can try that, drag that in, and make it twice as loud. I'm going to let you do that as a small exercise. So we want an amplifier here to have our output twice as loud. And you can use the multiplier with a constant for that. So I'm dragging in the operation here to multiply by a constant. You see that the connectors are blue, so that means complex, but we want to operate on real numbers, so you have to change that. So float. And then I remove this connector. And I drag this in. Okay. And now I hear nothing at all. And why is that? I'm multiplying with 0, so I have nothing. But if I change that into 2, then I multiply with 2. The nice thing about this is that you just can look at the output to see if it improves. Though, I don't know. Well, actually, this is if I point it to there. Yeah. Okay, so I need an assistant. No. No. You will want to play? Okay, well, that's great. Yeah. Sorry?
Try the side because we got pretty good results.
Yeah, I can try that.
Show me that side as well. Only where it
No, no.
What was the frequency? 91.3, I think.
Ah, you had another frequency.
Yeah.
Okay.
Somewhere around there.
Yeah, nice. I can see 2 carriers here, yeah, but they don't demodulate good. No. This one is a bit better, yeah. But I think actually for me the 100.9 is working best. Yeah. Okay, we'll leave it at that. Then you can follow along.
Could you remind me of the configuration for the phone?
Yeah. So you just, let me stop this. So I put in the waterfall sink, yeah. I change it to float, and then the sample rate, exactly the same sample rate as the audio sync. 48 kilohertz.
And then nothing else.
No, and connecting, of course. Of course, we work here with a constant. You can again work with a slider, and you can drop in a slider and use that to use as a volume control. I'm going to drop this one here because I'm going to put in another one. So this waterfall for the RF signal, I'm going to drop it. And I'm going to add another one for the audio. So this one here, the changes you have to make, float and sample rate, you replace it with 48,000, 48 kilohertz. And then now you connect this output here to here, and then you can play it. like this. And this one here is amplified, so you see a bit of difference. But I'm doing this to show something else. I want to introduce filters. Okay? So filters are they also exist in analog radio, of course. Filters allow you to filter out signals and to say what kind of signals you want and what kind you don't want. And I'm going to introduce a bandpass filter. Okay? And a bandpass filter is a filter that will only let through certain frequencies and nothing else. Well, of course, that's something you can do in a digital world. In an analog world, there's always something that goes through at very small values, but it's not digital. So I'm removing the multiplier. And I'm going to filters. And here, bandpass filter, this one here. You can drag this one here and put it between the demodulator and the audio sink, and then you connect the waterfall sink to the demodulator and the next one, the second one, to the output of the filter. So when you drag this in, you see several colors, some things to pay attention to, of course. Blue, we cannot use blue, we want orange, so complex numbers need to become real numbers, floating numbers. Sample rate here to 1.92 megahertz. That's not what we are working with. We are working with 1.92 megahertz at the RF side, but at the low frequency side and the audio side, we are working with 48 kilohertz. Always things you have to pay attention to, otherwise it doesn't work. So here you select float, from a floating number to a floating number. You have two options with decimation and interpolation. We are not going to set those parameters, so you can just select decimation and leave the default values. And we are not going to do resampling or amplification with gain or things like that. No. So just float, decimation. Here the sample rate 48,000. And now we are going to set this filter to simulate the frequency characteristics of the old analog telephone line. Okay? And that was between 300 and 3000 hertz. So you can put in here 300 and 3000. And then for the transition width here, you can put in something small like 10. Like this. And now you can connect this. So the demodulator goes to the bandpass filter, and the bandpass filter goes to the audio sink. And then you can also connect the second waterfall display to the output of the bandpass filter, like this. And then you can run this. See? And now this sounds like a low quality radio. I mean, first we had static, but static of high quality. And now we have static here of low quality. And you can see here, between 300 and 3000, we have data, and all the rest is blue. So that's filtered out. If you, yeah, the music that is playing now is of low quality, like it wasn't before. Those filters, of course, I put them here in the audio side because that's why I can easily show you the effect and when you listen to it with the audio effect. But of course, filters can be used all over the place as long as you use the correct values for sample rate, frequencies, matching of impedances. Okay, so this was a quick overview, an intro of what you can do with software-defined radio. And the advantage if we have some radio stations is that you can even have more fun doing it. Here it's just a bit of static. But it shows you that with those devices, if you are in a less noisy environment, and I'm talking about radio frequency because I think there are a lot of radio frequency here, maybe like, for example, my transmitter, maybe. But that with some simple devices like that, because I think a couple of years ago I bought them around $10 piece. They're probably even cheaper now, that you can still have some fun. Also, if you want just to experiment with those audio sync and things like that, you don't even need a source, a device. If I can find it back somewhere in there, have to be signal generators. Waveform generators here. See? If you are interested, these are components you can play with. They allow you to have a signal source, for example, sine wave, a simple sine wave. And then you can try out the different filters, so what that gives. What I did also, for example, is, sorry, I forgot the name in English. It's a specific radio term where you have two signals that are very close to each other, and then they interfere with each other. And no. It's what you have is if you have those. So you have, for example, a signal at. Sorry. No, not harmonic distortion, but 1000. I'm not on Wi-Fi. Is someone access to the Wi-Fi? Yeah. If you can go to the Dutch Wikipedia, and I can find the Dutch word, and then we can switch. Beatings, that's it. Beatings. Yeah. So beatings. So the thing is, you have a wave, for example, of 1,000 hertz, for example. Another one that is 100,001. Sorry, so 1000 and 1001. If you put them together, yeah, you will have beatings. So you will have a noise that slowly amplifies, becomes louder, and then slowly becomes slower again, lower again. So and it. We call it zwevingen, so it's something that floats. See, it all floats in and out, and that's something that I was able to do with this. I just put in two sources, two signal sources with a slightly different frequency, combine them, then have my displays with my oscilloscope, and then you can actually see the waves that are evolving. So even if you don't have any hardware, you can still do some things with GNU Radio. Okay. Okay, thank you for your attention then. I would like to get my devices back, so the USB sticks and the dongle stick.
You're only tuning the radio to about 675 megs, which is your radio.
Oh, I don't think my device goes that low, the SDR that I have. But we can try, eh?
609.775.
So let me say that the minimum is 1 megahertz. And you say that it is 6 megahertz, around 6 megahertz? 6. 609, yeah, okay. I was already thinking that 6 megahertz is really low. that's what my power boosted Apple computer had, the Apple II I mean. I had 1 megahertz and later on 6 megahertz.
Works. I can hear you.
Oh, okay. 600, and let's do 601 and 100, and let's like this.
Yeah. I guess just as small as that. I'm guessing. So you would have to be a big stall.
No, let me put in the waterfall for the RF.
Yeah, that's it.
You need to get rid of your bandpass field as well, that just making it sound right.
Crank up the volume.
Oh, no, that's the wrong one, sorry. It's a waterfall. No, I can hear the beating that it's oversampling on my machine. Okay. But I have something, yeah. So that would be around 608.4.
609.775. 609.775.
Yeah, I know, but he didn't take it, probably because, yeah, it's outside this. Yeah, you see, but the sampling rate is not high enough to. But we can still see something. Okay. Thank you.